So yesterday we took notes on the basic simple machines, and then we went further and we looked at how those machines give you an advantage, how they make it easier to do work. Who can tell me what the formula is for work? What does that mean? Force times distance. So when I'm doing work, I have two choices. Let's say I'm lifting that 1,000-pound dumbbell or barbell. I can apply a large force, lift it all up, boom, do it at once, maybe 1,000 newtons of force, and I apply that over, maybe 1 meter of distance. Or I can do it a little bit at a time. I can take that barbell apart, boom, only apply maybe 1 newton of force. But I have to take a lot more trips back and forth, back and forth. So maybe it's going to take me 1,000 meters going back and forth to get the same job done. Do you all see that we have done the same work? That in both cases the work is 1,000. In one case I'm applying a little bit of force over a long distance. In the other case it's a lot of force over a shorter distance. But it comes out the same. That was the main concept in terms of work. The other concept yesterday had to do with mechanical advantage. And what is the formula for mechanical advantage? Mitchell? Yes. When we look at a machine involves putting some work into it and the machine gives us work out. Okay? For instance, a pulley system. The work that goes into it is me pulling on the pulley. A lever. The work that goes into it is me pushing down on one end of the lever. Gears. Me cranking a gear. Okay? That would be the input force. What the machine does for me, what it actually lifts or moves on the other side, is the output force. And the whole purpose of machines is to make the job easier. But there is a trade-off. If, for instance, this machine makes my job easier, what is the mechanical advantage of this machine? This pulley system? You should be able to tell me. 2. Remember the rule was you count the number of rope segments, not including the last one that the force is attached to, and you have the mechanical advantage. So I already know that this gives me a mechanical advantage of 2, which means if normally all I could lift is 50 pounds, with this machine I can lift 100. It lets me do twice as much. So if I put in 50 pounds of force, or let's say 50 newtons, that'd be a better label, the machine is going to allow me to apply how much force? 100 newtons. What I put in and what I get out, the out is going to be twice as much. The trade-off here, though, is I am able to apply twice as much force, but I must do what? An exchange. Nobody got this. This was the main idea from yesterday about mechanical advantage. All the machines, whether it's a lever, a pulley, a wheel and axle, if you get more force, you got that in exchange for what? Longer distance. When you're using a pulley system, remember we had a lever even. If we have our fulcrum right here and our effort, that's pushing down right here. And over here is my resistance, my block. Okay? If I move that fulcrum farther away from my effort, what happens to the mechanical advantage? Does it go up or down? Does it increase the amount I can lift or does it decrease it? Increase. As I move this away from where I'm pushing down, it increases my mechanical advantage. But you'll see that it also increases the angle of that lever. So now you have to move it a lot further to move it just a little bit on this side. That was the idea of mechanical advantage. There is a trade-off. In the case of a pulley system, yes, you're able to lift more with this, but you have to be pulling that cable a great deal. You have to move it over a larger distance. So a long pull here will give you a little bit of distance here. But the trade-off is now you get to lift more than you normally could. When you have complicated pulley systems with a whole bunch of these and a whole bunch of rope segments, you might be able to lift 10 times what you could normally lift. You might be able to lift an engine out of a car. Well, in that case, you're going to be pulling a lot of rope to lift it just a short distance. That's the trade-off. And it was the case with all those, just like my lever here. How many think they understand that? You guys were awful quiet about that. All right, so we already talked about the pulley, how it works, and we also talked about the gear, how the gear changes what two things? Direction or speed. If we want to gain a big mechanical advantage, what can you say about the size of two gears? Two gears working together. What can you say about their respective sizes if you want to have a big mechanical advantage? Yeah. The bigger difference, if you got a really big gear here and a little one connected to it, the bigger the difference, the more mechanical advantage you will have. The big gear will have to move a long distance, but it'll give you a lot of force on the little gear, okay, or vice versa, depending on what you're trying to accomplish. And we talk about gear ratios. That's what we do in the car. That's what we do with your bike when we're trying to go uphill. As you're going uphill, suddenly it's so hard to crank those gears that you shift gears, and now instead of going like this and almost tipping over, you switch to another gear, a smaller gear, where you can pedal really fast, but now it's going to make the bike just barely move. You can keep going that way because you're applying a little bit of force over a long distance, and it's going to give you a lot of force over a short distance. Same thing in a car, okay? Now we're switching gears, no pun intended, to Rube Goldberg machines. And you might say, well, what does this guy in 1883 that drew comic strips have to do with simple machines and all the rest of this? Well, I'm glad that you asked. I'm going to explain. Reuben Lucius Goldberg in 1883 wound up later on in his life winning the highest prize in his field as a cartoonist, sculptor, and author. He became famous for these comic strips that you see over here on the wall, the long skinny ones, and I'm going to show you an example of that in a little bit. His career started when his father, a very practical man, insisted that he go to University of California at Berkeley to get trained as an engineer. You will be an engineer. You know, it's like parents say, you will be a doctor, you will be a lawyer, whatever. That really wasn't his dream. His dream was about as far away from being an engineer as you could get. Engineer is very scientific and practical. Artist is the opposite end of that. That's really what he wanted to be. Well, he did go to college. He followed his dad's advice, and it's a good thing because it's one of the things that he used later on to become successful. But he didn't want to work as an engineer. He started at the San Francisco Water and Sewers Department working as an engineer. Not too glamorous. But he continued to do his little drawings, and after about 6 months he talked his father into letting him go work as an artist. As you know, artists don't usually make a lot of money unless they become very famous. He got a job with the San Francisco newspaper, working as an office boy, just starting from the very bottom, but he would keep drawing his little cartoons, his little comic strips, and he would submit them. Finally, his editor agreed to have one published, and they were a big success. And in order to understand what he was trying to show with his cartoons or his comic strips, why they were so popular at the time, and still are today, you have to understand what was going on at that time. Okay, remember we're talking around 1900, 1910, 1920, in that range. Industrial Revolution. The automobile's making its way out into cities. People are getting blenders and ovens and all these different electrical devices that do all sorts of cool things. And the attitude at that time was that all these machines would make our lives so easy that we wouldn't have to do any work. That humans would just sit there and we would be served by these machines. And some of the stuff that was being sold was just ridiculous. You know, Let's say you need to put toothpaste on your toothbrush. I'll make a machine that'll do that automatically for you every day. Well, how hard is it to squeeze the tube onto your toothbrush? Yeah, you can make a machine that does that, but it's actually going to be more likely to fail and take more work to turn on the machine and set it up every day than it would be to take out the toothpaste and squeeze it on your toothbrush. But those are the types of things that were being sold at the time. Well, he used his background as an engineer, and what he was doing is he was making fun. It's called satire. He was making fun of these ridiculous devices that were out there and the people that wanted these machines. And as an engineer, engineers are taught one very important principle. Some of you may have been taught this principle. It's a great one. I use this all the time in life. It's called the KISS principle. Does anyone know what that stands for? K-I-S-S. It's going to be my first class today that doesn't know the KISS principle. This is advice that every engineer should follow. You know, an engineer is going to have to design or build something or maintain machines. So if you're going to sit down and you're going to design or build a machine, you want to follow the KISS principle. Keep it simple, stupid. Because the tendency of someone that knows all about these equipment, all this kind of equipment and machinery, is they make it overly complicated. It's kind of like you talk to a scientist and they explain something to you and you're more confused than you were to begin with because they use all these fancy words and they make it overly complicated. That's what was happening with a lot of the machines. You know, a simple task was now being done by these complicated machines. They weren't following the KISS principle. They weren't keeping it simple. Let's say, for instance, we need to make a machine to pump water. Okay, I want to make a pump. Matt makes his machine and it involves 4 parts. I build my machine to do the exact same job and it involves 40 parts. Well, which one do you think is going to be more reliable? Matt's, the 4-part machine. There's fewer things to go wrong, to break. And engineers are told to keep things simple, not make it complicated. And so his whole cartoon or comic strip was pointing a finger and making fun of man's capacity for exerting maximal effort to achieve minimal results. I say, Mitchell, go outside. He should get up and walk in a straight line to the door to get outside. He shouldn't jump up on his desk, go, woo! Smack his head, run around in a circle, jump over there, and then go out the door. That's a waste of energy, okay? We want to use minimal effort to get the job done as an engineer. So the cartoons or comic strips that he drew, they showed these highly complicated machines that you could just look at and figure out how they worked. And you've seen machines, devices like this in the movies. Back to the Future, there was a machine to feed the dog that the professor had made. Chitty Chitty Bang Bang, there's a machine to make breakfast. I'm sure you've seen this in a lot of other movies. I can't think of more recent ones right off the top of my head. But they would have a ball would roll down and trigger some dominoes, which would hit a switch, and the fan would blow, and the fan would blow this thing into that thing, which would knock that over, and so on and so on. He would draw illustrations of these kinds of machines. Okay, and it became so associated with his name that nowadays any machine that shows a really complicated solution to a simple problem we call a Rube Goldberg machine. Here's an example. I particularly like this one. Now this one doesn't just do one thing. It actually does a number of tasks. Look at it and see if you can figure out what this machine accomplishes. Megan Lynn, you got it? No? Zach?
It wakes the guy up and gets him dressed and puts him in his little chair so he can have breakfast that it made.
There you go. Does all of his morning tasks. Now, in many cases, the Rube Goldberg machines would just do like one thing. It's raining outside, so it automatically closes the window for you. Again, it's a simple task, but it would close the window in 25 simple steps, whereas you could walk over and close it in 1 step. That was the whole point. He was making fun of these ridiculous machines. Now, if you're not an engineer, it may be hard for you to follow the whole action here, so let me talk you through it here real quick, and I do mean quick. Newspaper comes in through the door, pulls down on the tray pulls through the pulley, knocks the ball off of the plane into the basket turns one gear one way, these two gears opposite directions to pour the milk and the cereal into the bowl through the funnel. As this gear is turning this way, it also lights a match, which lights the candle, which heats the coffee. It also heats two pieces of metal made of brass and iron, which Rube Goldberg knew would cause it to bend. It would then bend and tip the coffee into the funnel, which would fill up the cup. At the same time that's happening, the lever here would push the mallet to strike the push rod, which would hit the cannonball down the decline plane to hit the bell to wake him up to go into the displacement jar to raise the water level to rain down and start the shower. At the same time that was happening, this lever would go up, knocking the heavy weight into the bucket would fall off the decline plane, pull through the pulley, lifting his bed, sliding him down the decline plane, rinsing him off, sponging him off, toweling him off into his pants, getting combed right to the top of his head, into his chair, there's his shirt ready, right into his shoes, breakfast ready to go. Simple, right? That's all that machine does. Now, one thing goes wrong. That little ball doesn't go down the decline plane. All the rest of this doesn't work. The newspaper boy puts it in through the slot and misses that. The whole thing doesn't work. So if you were to actually make one of these things, it would be pretty impressive to watch. It would be quite the accomplishment. Go on YouTube, type in Rube Goldberg machine. You'll see all sorts of these. Some of them are just outrageous. And if you're an engineer, and you know something about physics, you really appreciate how hard it is to build these. This is the opposite of how we should design a machine. We shouldn't try to make it as complicated as possible. We should try to make it as simple. But if you can make one of these and have it actually work, that's quite impressive as an engineer, to be that skilled to make all those things work. Because one step fails, the whole thing falls apart. His inventions, his illustrations became so popular that in 1949, this was the peak of when these cartoons were really popular, two engineering fraternities at Purdue University, the Phi chapter of Theta Tau fraternity and the Triangle fraternity, developed their own Rube Goldberg machine contest. They said, you know, you do these things on paper, they really should be buildable. We should be able to make them work, but it's going to be a major challenge. So what we're going to do is we're going to have a little contest and we're going to create some simple tasks, like putting toothpaste on a toothbrush. Now that could be done as simply as having a bowling ball fall on the toothpaste, right? Squirts out the toothpaste and it hits the toothbrush. There, you're done. But what they did is they have to work backwards from there, and let's make it more complicated. How are we going to make the bowling ball fall? Something's going to knock into it. What's going to knock into it? Okay, maybe, you know, a lever will tip it up and that'll allow it to fall. What's going to raise the lever? Well, a pulley's going to be pulled down. What's going to pull the pulley? And they would design these machines, like the one you just saw, to be as complicated as possible. And then see who can make the most complicated machine. Now, that's not how you're supposed to design machines, but if you can make a complicated one work, you can definitely make a simple one work. So it became this little challenge for the engineering students. Now it's become so popular that the winners of this contest, it still goes on today, it's held around the world and they all come to Purdue to compete, that the winners are seen on all these TV shows. And in 1988 they had the first national contest there. They have more people attending this event than football and basketball games. It's a one-time thing. And it's very, very popular. Now they do it in other colleges, they do it in high schools, they do it in middle schools, and even elementary schools have Rube Goldberg machine contests. We're going to have our own little one here. And I'm going to show you some samples here of what other middle school students have achieved. But the whole point was to show the contest, was to show the need for keeping things simple. That when you get complex, it's really hard to make things work. If you can make a complex machine work, though, you can do anything. But that's not typically what you'd want to make. Okay? And now, it's your turn to build one. You're going to be working as part of a team. Before you even do that, you're going to design your own. Like Rube Goldberg did, you're going to draw a little comic, a little picture. representing a machine that does some simple task. And I'll tell you more about that here in a second. But first, let's take a commercial break. So what's the purpose of the machine?
Wake her up. He's gonna wake her up.
With an axe? I don't know if that'll wake you up. This is too far. So that German sense of humor is a little different than American sense of humor, but
You didn't ask if I left that.
Zach was right. Yeah, Mr. Waker up.
Yeah, that's how you dies.
All right. So obviously that's not the kind of Rube Goldberg machine we're going to make in here. But I am going to show you some samples here. I'm not going to show you all these in the interest of time. We have another little hands-on opportunity. I'm going to have you go to your stations here a little bit later, and you're going to use some supplied materials and some supplied directions, Zach, to make one of these so you get a feel of what's involved in it. Because seeing it and having an idea on paper and actually building it are two, three totally different things. But these are examples of ones built by, like, I think they were 7th grade students, and they didn't even get to work in teams like you guys will be able to do. They had to do them individually as like a homework assignment. In addition to building them, they had to explain them. Tell me, what are the levers involved? Is it a first or a second or a third class lever? Were there pulleys? Was there a wedge? And all the different machines that we've talked about, they have to point those out and how it works. And when you've actually built one of these things, then you understand all the physics that are involved that we've talked about. Okay? So I'll show you the food catapult here first. Yeah, they did that in Home Alone too. You're right. You're right.
Catapult, and I'm catapulting M&Ms. And the way it's supposed to work is I turn the crank, and then the strings come around the pulleys, and the strings are attached to the wheel and axle, which rolls up the inclined plane and up the third class lever with the fulcrum and the effort and the resistance. And then it gets pressed down onto the spring, which is this screw, and it keeps rolling until it gets off the edge, and then when it gets off the edge, the catapult will launch the M&M out the door. Okay, and so I have fixed pulleys here, and 2 inclined planes on the sides, and a wheel and axle, and a lever, and a screw, and the wedge, which like points the direction that it's going to be thrown. Okay.
And the spring does not function as a screw, but that's what she called it. That wouldn't really be accurate. Let's do...
Our project is the Acme Automatic all-purpose shower. And what it starts off is that a steel ball will drop down the screw, powered by a wheel and axle, and will travel a declined plane, going up an inclined plane, landing in the bucket, moving this up, unbalancing this lever, putting the steel metal ball onto the mouse track will snap, and the bar little thing will hit this, will make this uneven, and water will hop into there with a bucket full of nails and holes, and shower the silver surfer.
Alright, I'll show you one more. You tell me which one you want to see. I can go back to the previous one. Toast cutter? Okay. The flag raiser is mine, by the way, and I'll show you the real thing, hopefully, tomorrow. So you don't have to just get it from the video. The video's online, by the way.
Put the marble down this, and goes down my screw, and goes into the cup, and then that makes this go down, and then that releases the car, and then the knife goes down and cuts the toast. And that's my screw, lever, first class lever, effort, fulcrum, resistance, inclined plane, and pulley wedge. Oh, my name's Danny Zhang.
Some of the machines go real fast. Some of them go a little slower. It all depends on how you engineer it. All right, so here's what we're going to do next. Before I tell you about what your specific challenge is for this class and give you the rules for how to build a machine and talk about the homework, I want to give you a chance to actually see what it's like to make one yourself.